Introduce you as. Hello, I'm Bree Oatman, and I'm the Education Director for the South Dakota Discovery Center. And today we are doing another remote learning hack. And once more, we're focusing on some modules that are available through the South Dakota EPSCoR STEM education portal. The link to that website is found on our page. And today we're going to be focusing on a module that looks at material science and engineering. And my guest today is Dr. Namika Prasad from South Dakota State University. And she is working with NASA to do some research on 3D printed metal alloys that are used for specific components in spacecraft. And so I'm going to hand it over to her for her to talk about what she does. And then we will demonstrate an activity that you can do at home.
Yeah, thank you, Bree. And, thank you for having me here. It is exciting to share this research with all of you. I got some samples to share also, but I'll walk you through. I saw the EPSCoR educational material that has been prepared, and it's so much detail. It's such an exciting thing to see everything in detail. So I'll not talk a whole lot on the background, but kind of add on to whatever information is already out there. So you can see my slides, I guess. If you can share, I have some images to show. Yeah, thank you. So this sample, the image right here, shows a sample that we get from NASA. And if you can see my, my picture also. So here, yep, here is a piece from that sample. So this looks black, but is actually a large percentage of that is copper. So it's a copper-based alloy. NASA has been working on copper-based alloy for rocket engine as a heat, as a material for the rocket engine for a long time. The newness is that they're now printing it using the new technology called 3D printing. So our focus here is on analyzing the material, the 3D printed material, and how changing the parameters influences the property. So it's not sent to us in the form of a rocket engine, but it is sent to us in the form of this shape, right? Any piece, like they printed out the thickness and all, that's what they're trying to replicate, and we get samples here. So that's what the image here shows up. And on the bottom is a screenshot of a paper that I'm working on. And I wanted to put it there so that students get an idea that, anytime we do a project, it is not just one person who is working on it. We have a team of students working, team of scientists working together. So I would like to highlight, for example, Paul here is, they're from NASA scientists, so that's who gave us the material. And then the first two names are the students who are doing a lot of tests with us. And my name is at the last, where the project advisor for this particular portion is usually at the last of that paper work. So there are a lot of people working together, and some of the images that I'll show you kind of walk you through what is the outcome that we get out of it. So we are interested to analyze this material. In the lesson plan, there's a lot of talk about alloy design, and so I thought it would be a good idea to kind of connect with that. So in one of the images for a periodic table, and it is drawn for image at a temperature of 2000 degrees centigrade. That means, what are the materials in a solid state and a liquid state, right? So many metals at that high temperature become liquid. So the choice of alloy is to get that right property so that it does not melt at that high temperature. At the same time, it has a right strength, right ductility, and all that. So and thermal conductivity, of course. So those are the yellow here demonstrate the combination, the alloy design. And then I'll talk to you about what we are doing. So when we get material like this, again, the same material that I was showing you, and if I rub my finger through it, it is very rough, and I had sent some samples, and if you are doing it in your class, you'll get some samples for that. So it's a very rough material. And the reason it is so rough is the way the 3D printing works. So it's printed in layers, you get that feeling of the layer. So we want to analyze how the as-built sample is. And the image here shows a laser image of the surface like this. So I would take a small area, we'll take it under a microscope and look at laser image. We can do a whole lot of analysis only on the image itself. We can find out what the roughness is, what the thickness layer is, and all that. So here is a 500 micron by 500 micron size, and the bars here gives you average roughness across 3-4 different lines in the whole area. So we do analysis and find out, if you change 3D printing parameters, how does it change as built parameters? So that's the reason why we would do roughness calculations. And then we do a whole other bunch of tests. We know it is the alloy composition, but it's when you design new material, it's not just what percentage of those materials are in the sample, but it has also to do with the structure. Right? So if you have copper and chromium, what is the distribution of copper and chromium in that structure will influence a lot about the property. It's called a microstructure. We look through at we do another level of imaging to understand the distribution, not just what is present. So the table shows, okay, we have these chemicals, these elements present, and these figures kind of shows where the chromium portion is. Copper is obviously everywhere, but dots will show where the chromium is or where the niobium is, and you sometimes have other trace elements also present. So alloy composition analysis also means not only finding the composition, but the distribution and internal structure in that. So we try to do that through various tools available here. Many other tests. So we want to know how the material will behave under that high pressure. We want to know its tensile strength at different temperatures. So this might not be very clear, but these two ends, you put your sample between those two holders, and we pull it and find out how that behavior, what the metal will behave. So, again, we take some strips from that. We'll cut strips from this original material, make it into a tensile sample, subject it to a machine called tensile testing machine, and there is a heating element, so we can test it at different temperatures to find out its failure, when the failure will happen. And these samples kind of shows a failure. And then, I'll not take a whole lot of time describing different tests, but we do a test at different scale. That's another way we prepare our sample. Yep. So in order to take it from the small scale imaging or microstructure, we take the sample, embed it in an epoxy, polish it, and then we do laser microscopy also. And we can also check the hardness at the small scale, which is called indentation testing. So large scale, different small scale. So here are small, indents on a surface like this. And that also gives us information on the mechanical property. And now we are moving on to use computer tools. So we can do as many tests. We get smaller samples. And this is, so in addition to experiments, you can do computation. You can do math to understand how this material will behave or predict how changing one parameter, the laser energy, for example, will influence what changes we can get in the structure. So that's our next step. We are continuing to do the experiments, but at the same time, we also use underlying mathematical tools to predict what that behavior will be. So, so those are the various approaches that we are helping NASA in developing and optimizing the manufacturing process of these 3D printed materials. And just 2 more slides in general. So my lab, my lab is called BioM Lab. We do a lot of work on high-grade materials, like the NASA 3D printed materials, but also with biological materials. So if you're interested, that's where my link is. You can learn more about other things that we do in our lab. And the link is here through my lab, my first and last name.com, or through SDSU's site, the external link. is here for my lab, but both of those websites are connected. So that's all I have to, kind of share of what work we are doing here, and I'll happy to answer any question, Bree.
Thank you. We'll make sure that the link to those sites is put up on our Facebook page as soon as we're done streaming here today. And so now what I'm going to do is I'm going to connect what she just talked about with some activities that are actually in the module. So if you were to do the module in its entirety, it starts out talking about how we classify matter, and students are introduced to the periodic table and kind of the history of how a periodic table was created and the different families and groups of elements. They're asked to kind of create an analogous world map of the periodic table where they think about the different families and their properties and how that would be analogous to different cultures, interactions politically, economically, socially between different countries based on those properties. And then the students actually learn about metal alloys and thinking about the different compositions of alloys and how the compositions of those metals actually change the structural properties. They also do some investigating about different types of the different chemical and physical properties of the groups of elements. And through that process, they're basically kind of eliminating options for what would make a good heat sink. So the whole time they're thinking about what type of material would make an optimal heat sink for a rocket engine. The phenomenon actually at the beginning of the unit, and the videos are available in the module, is a YouTube video about how NASA used active heat sinks for their space shuttle program, where they would actually coil the rocket. The combustion chamber actually had metal coiling where they would run the liquid hydrogen around that to cool it. And then that would allow the hydrogen to turn into a gas before it went into the chamber to be combusted. And there's a really great video about that. And the guy who does the video actually has a presentation where he actually boils water with a coiled pipe system where he's keeping ice cream from melting on the pipe as the water's boiling on the inside. And then there's a couple videos that also show NASA testing some of these combustion engines that they printed with the 3D metals. So the students engage in a variety of different activities kind of relating back to what Anamika is researching. And two of the activities in particular would be really easy to do at home. And those are basically lessons 7 and 8. So lesson 7 gets students to think about how when you combine different materials to get optimal types of properties, whether it's tensile strength or durability or ductility or lack of reactivity or whatever it is you want your properties to be, you're kind of combining, you're changing the properties overall. Like there's a trade-off. You can't keep everything that you had with copper and everything you had with chromium when you put them together. And so I'm going to model that with my NerdCam. So I have basically set up different, so what I've done is I've created a couple of different examples of composite material. And so one of them I basically just have saran wrap, and I have some saran wrap, and that saran wrap has string and some crepe paper glued on the inside. And then I have a piece that has nothing in it. And then I did something similar with paper. And I basically have the string and crepe paper inside 2 pieces of paper plus a normal piece of paper. And so you can have kids kind of come up with their composite materials and then do tests just like what Anamika was showing in the video. So it could be things like trying to tear it. You could be trying to pull it and look at tensile strength and seeing how hard it is to pull it apart versus pulling apart another material. And then it could also be things like trying to twist it, seeing if it's waterproof, all of those different kinds of things. And then the other thing is that you can have students actually create a device that would kind of model a combustion engine where they have to think about how you would use a heat sink to try to remove heat from that system so that your combustion engine doesn't melt. And so in this case, I have a small container that's wrapped in foil, and I have another container that has a, my brain just, I have a paper towel, and then I have more saran wrap. Sorry, my brain just escaped me. And I have some ice cubes. So I happen to have a kitchen scale, and so you could weigh your ice cubes before and after, but that isn't necessary. You could also just have kids put the ice cubes in, and then time how long it takes for the ice cubes to melt in each container. You could also figure out the volume of the ice cube before and after a designated amount of time. If you had thermometers, you could look at temperature. But basically, the idea is if you have a really good heat sink, it's going to be pulling that heat energy out of this system, and that ice cube should melt slower than an ice cube in the other one. And so, and the idea is because it's pulling that heat energy away from the ice cube, then you should see less heat energy going into the ice cube to melt it. And so those are just a couple of examples. If in the module's entirety, students might also then do some reflection activities on their engineering design and how they could improve the design. And then there's some career exploration activities as well, where students could use the internet to research different types of careers related to material sciences, engineering. And then there's additional resources in there that connects kids to NASA and in the work they're doing related to 3D metal printing, metal alloys, and how they use those for space flight. So thank you for joining us today. And if you have any questions before we sign off, if anybody's watching live and has questions, we can take those now if you want to add those to the comments. And if not, we will say goodbye.
Hi, this is Ann in the booth, and no questions from our social media people yet.
All right. Well, Anamika, do you have anything else to add before we go?
No, I mean, that's again, I'm excited to be a part of it. And anytime they have questions, follow-up questions, I'll be happy to answer it. There is also a kit designed by, for NASA at my library. And I can send you a link. I don't have the link. But the idea was the same concept of showing how metals conduct heat. So we had copper and brass and one more alloy. And there was a small sensor attached to it to show how the heat conduction happens visually. So I can send more details to you, and you can share it with others of how to get those kits.
Okay, thank you.
Okay, thank you.